Welcome back, everyone. Now we have the second talk for the day by Lorenzo Zambotti. We'll speak about weighted norms and a priori estimates for rough paths. Please, Lorenzo, go on.
Thanks, Nicolas. So I'd like to thank the organizers for the invitation. This is going to be a very basic talk, probably even without new results. But so, you know, after working with Francesco Caravenna on the reconstruction theorem, well, so one of the sources of this result is the semi-lemma, and well, so therefore we were thinking also of this result and connections, etc. So one of the main applications of the semi-lemma is in rough differential equations, and there were some lecture notes by Massimiliano Gubinelli on rough paths, which are still so available. They are very, very dense. They contain a lot of ideas, some of which are somewhat only sketched and need some work. So we started to do this with him, and so this is still an ongoing work. Okay, so I will share with you some of the ideas which we are working on, and yeah, unfortunately, as I told you, at the moment, I don't think we really have new results, but this may come later. So let me, yeah, remind you of some very basic classical stuff. So this is the setting of a ODE in some Euclidean space with a Lipschitz map B. Okay, so this is the ODE. Now, the classical approach is to use some fixed point method in the Banach space of continuous functions with values in RD. And usually, so the first idea is to use the sup norm of F in this space. But then if you want a contraction, you need the time horizon, capital T, to be small. If you don't want to consider a small interval, you want an arbitrary interval, then you have another classical method, which is to use this weighted norm. You introduce another parameter tau, positive, and you consider this supremum where you multiply f by this exponential factor. Okay. Now, in fact, you can find a tau small enough, which actually depends only on the Lipschitz constant of the coefficient b, such that you have a contraction for any time interval 0t. Okay, now I'm presenting the ODE setting, but this also works for SDs. Okay, now let's move in the direction of rough differential equations. So we consider a smooth, say, C1 path X, a coefficient sigma, which is now with values in matrices, and which is smooth, and we have this controlled equation. Okay, now this is the, say, the smooth version of a rough differential equation, even if you want a stochastic differential equation. And you can see that you have a Taylor expansion in time of the solution y, which gives you this expression. Okay, and you see these two terms which appear, which are now the the rough path, so at least one rough path over the path X, etc. Okay, and you have this chain relation and this analytical condition. Okay. So I'm sorry, I'm just reminding you of the definition of a rough differential equation, at least the simplest possible definition. So now if you consider a X which is only of class C alpha, so typically the first case of interest is between 1/3 and a half, then you can generalize the previous slide to a rough path which satisfies this condition. Now alpha was 1 in the previous slide, this has become now less than 1, and you still can discuss existence and uniqueness of solutions to this equation, where again you have alpha here, which was 1 in the previous slide, and now it's less than 1. And so you are in the setting where still 3 alpha is bigger than 1. Okay, so it's very important. Otherwise, you need a longer Taylor expansion here. Okay, so this, if I understand well, this is a notion of solution which is due to Davy. So anyway, this has become the one, maybe the most popular definition of a rough differential equation. Okay, so we are going to discuss essentially a priori estimates on this kind of object. Okay. Now, norms. So in my title, I mentioned the weighted norms. So the first standard norm is the following. Okay, this is so. Okay, you introduce controlled paths which are given by pairs of maps. So y is the first coordinate. Y1. Okay, sorry. Notations are vary from authors to authors. So here I have chosen this notation. Y1 is the first say term of the expansion, and then Y2 is this remainder. Why is that reasonable? Because Y1 has regularity, say alpha, so not a regularity. Say you have this bound with alpha, and Y2 has this bound with 2 alpha, and then so one possible norm on the pair is this one. Okay. So in fact, one can see that a solution in the sense of Davy has the following property, that y comma sigma of y is a controlled path. Okay. Now, if you use these norms, so again, just to be more compact, you for any positive eta and any function from say 2 time variables to RD, you can introduce this norm or this. No, yes, here it is a norm. At least, okay, F should be continuous, but okay, anyway, this supremum, okay, and then you introduce this other notation delta equal to yt1 minus 1 minus s. Then okay, what I defined in the first in the previous slide was just this quantity. And okay, so there are 2 estimates which are at the basis of all computations you can make on these rough equations. So the first relates the sup norm of a function of 1 variable with this kind of Hölder seminorm on F, okay? And here you have this T to the eta, which appears. And the second is this one. So if you have two functions of two variables, and you have two different here exponent, eta prime and eta, then you can relate one norm with one exponent with the norm of the other exponent by this inequality, and you again obtain this factor which contains a power of capital T. Okay, and essentially you use these inequalities a series of times until you can decide to make this capital T small enough, and for example, this is what gives you a contraction in the space of control paths if you want to do a fixed point result to construct, to have existence and uniqueness of solutions to the equation I mentioned above. So yeah, the drawback of this approach is that you have to consider a small interval and then glue together the solutions to have a solution on a larger interval, etc. So this is doable. There is no real problem, but okay, sometimes for aesthetical reasons, it would be nicer to have just a result on the whole interval. And besides, also the control of the constants sometimes is a bit hidden when one does not do it explicitly. So I'm always a fan of what, so a supporter of what Perstei-Iaconis says, that constants in the inequalities should be as explicit as possible. Yeah, okay, this is what I have just said. So the drawback of the above setting is that the arguments are local, and then the transition from local to global requires additional arguments which are, okay, sorry, usually tedious and maybe unelegant. Okay, and moreover, of course, you need in this transition from local to global some a priori estimates, because otherwise you may have explosion of solutions, and these have to be global. So in some sense, there can be a more satisfactory approach, even if, again, so this is done, okay? I'm not saying that the literature is missing any of these proofs, okay? But still, sometimes we have felt that there may be a more elegant approach. Now, these are the weighted norms I have announced in my title. So again, I have small f, which is a function of one variable, capital F, which is a function of two variables, and then I have two parameters. Eta is the exponent, say the kind of regularity exponent, and tau is the time scale. So the F infinite, sorry, the kind of subnorm of F is, again, as for ODEs, the supreme of F multiplied by the exponential factor. And now, so this is what may be new, is this definition of weighted norm for the increments, no, sorry, for a function of two variables, f eta tau. Now you have to take the standard here fraction, you multiply by an exponential factor. So very often you assume that s is less or equal than t. Here I don't do this, and then I just have the supremum of the two. And then you have to oblige, force T and S to be a distance less than tau. Okay, so this is, I don't know, maybe somewhat surprising at first, but it turns out that this works very well in the following. So now the relevant estimates that I mentioned before are the following. This modified sup norm is bounded by F0 plus now 3. There is a 3 here, which comes from the computation. Don't worry about that, it doesn't change much. Then you have this increment, okay, and then you have this factor. So you remember in the classical estimate, you have capital T to the eta. So here you have tau inf capital T to the eta, which means that you can choose either you take a T which is small, and then essentially you don't need tau, or you fix T and then it is tau, which is small, and then you get your for example, your contraction, etc. And the same happens for the other estimate. Instead of capital T, you have tau inf T. And you can also notice that, in fact, you can somewhat recover the classical setting just by taking tau, which goes to plus infinity. Okay, so you are not really losing, because, of course, the exponential goes to 1, and this also goes to the indicator function also goes to 1 and disappears. Okay. Now, what is nice is that you can repeat essentially. Well, okay, there is another ingredient, which is the main estimate, which is the semi-lemma. Now, the semi-lemma holds with these norms, and again with a constant which is uniform in tau. So let me remind you quickly what this is saying. So you need a third weighting norm, which is of the same nature. Now G will be a function of 3 variables. Again, you have eta and tau. Again, I do not suppose that SUT are ordered, but you may if you want. It's not a big deal. And okay, I write it like this. It's very similar to the standard norm, but again, you have an exponential factor, and then you are forcing the times to be close. Okay, distance at most tau, at least T and U on one side, and U and S on the other side. Okay, and then lemma. So again, this is the version of the semi-lemma in this context. The semi-map, sorry, I don't, for eta greater than 1, of course, is for the semi-lemma. I don't give you the details, but anyway, the semi-map has this standard control with a constant which is uniform in tau. So this is trivial. In fact, there's nothing to do after you know the classical semi-lemma, but it is of course very comfortable. It means that you have all the tools that you have without the weight and without the indicator function here, with the constants which are uniform in tau, and therefore you can repeat all the estimates, all the result, or the proofs at least, but on a fixed interval 0t. Okay, so now let me start with some results. So recall that we are studying solutions to this kind of problem, where this x is a rough path, and with 3 halves are greater than 1. Yes, I use this notation sigma 2 equal to nabla sigma times sigma. Now, theorem. This is the uniqueness. Now, suppose that you have 2 solutions, y and y prime. Suppose that sigma is of class C3, but without any boundedness assumption. Then, if you consider tau, which is small enough, and this small enough depends on y prime, on sigma, on x, and everything. But anyway, once you have fixed this data, you can choose tau easily. Then you have this, again, you may say it's a kind of a priori estimate. The sup norm with the exponential weight of the difference is bounded by 2 times the difference of the initial data. So in particular, of course, if the initial data are the same, this is 0. And therefore, you have uniqueness. Okay. So what is nice here is that you do this without boundedness assumptions on the coefficients of sigma. You don't prove uniqueness by a fixed point. So it's a kind of a priori information on your equation. Okay. So the fixed point is set up later with stronger assumptions on sigma. Now, another nice a priori estimates. So here you need to know a bit more. So suppose that sigma and sigma 2 again, which is nabla sigma sigma, are of class C1 and globally Lipschitz. Okay, so you fix now constant L, which is greater or equal than this, the sum of these two norms. You fix this quantity which depends only on x, so the rough path. And then there exists epsilon, sorry, which depends on m and l, such that if your rough path is bounded, okay, by this constant m, and your how do you say, your small parameter tau if t to the alpha is less than epsilon, then any solution to 2, so this is our rough differential equations, satisfy this bound. Okay, so again, you remember this is this kind of alpha Hölder seminorm of y. So this is the remainder of the control path, which is of order 2 alpha. Again, these are the weighted norms. Okay, and on the right hand side you have a very simple and explicit expression. So rho alpha, which is this, times this, which depends only on okay sigma and the initial datum y0. Okay. Yeah. So this, I don't know. Maybe this was already known. As I said at the beginning, we don't really claim any new results for the moment. If you already knew this, I'm interested. You please tell me. But anyway, this looks very nice, at least compared to other a priori estimates that I have found in the literature. Yeah, again, you see this is true on an arbitrary interval 0 capital T. Of course, capital T appears also inside the norm of this kind of, say, norm of the rough path. Okay, but once capital T is fixed, this is completely general. Okay. Okay, this a priori estimate is one of our results. So the second, say, result, or which is again not new, but we think that with these weighted norms, the approach is particularly nice. Is the following. Okay, suppose that sigma is of class C3. Okay, this is a boundedness assumption on the 3 derivatives, but not, okay, sorry, this maybe I may have stressed also here. Here it is not assumed that sigma is bounded, okay? So this, it's the moment to stress this. If you open a random paper on rough paths and rough differential equations, almost surely you find the assumption that the coefficient is itself bounded, okay, or that it is linear. So it seems that there is this kind of union of 2 settings. For example, you see here that, of course, if sigma and the derivatives of sigma are bounded, in particular, you see that this becomes completely bounded, does not depend on the initial condition. So when you iterate your estimate, this is particularly nice, etc. At the same time, this is not very satisfactory because you would like to have, like for ODEs and for SDEs, results which are true for coefficients with say linear growth at most, okay, like Lipschitz, globally Lipschitz, but not bounded. Okay, so we have tried to work in this setting, and again, it seems that although this is not new again, but it seems that with these weighted norms, this is particularly simple to treat. So again, I consider sigma, which is of class C3, with a bound on the first, second, and third derivative of sigma, but not on sigma itself. So I fix L, which is greater or equal than this. And so I have a statement on the continuity of the Ito-Lyons map. Let M be positive, then for every time there exists so a constant and an epsilon, such that if tau, sorry, this tau hat should be epsilon, such that, so any pair of solutions, now the solution here is the rough path and the control path, because you want to change also the rough path. You want to, to control uniformly these quantities, and then you have this, okay, again, it's kind of a distance in the space of control paths, but where now the basis, the rough path is allowed to change, and on the right hand side you have the what you expect. Okay, we have the difference of the initial data plus this kind of distance between the 2 rough paths. So you have the result of Lipschitz continuity of the Ito-Lyons map from rough path and initial data to control path. Again, this is not new, but we are particularly pleased by the somewhat say the elegance of the proofs in these weighted norms. So by the way, I had a very busy week, and I wrote these slides like 1 week ago. So in the meantime, I discussed with Antoine Leger, who has written, in fact, long ago, a very nice paper. So in 2012, where he has stronger results than what I'm telling you. So in fact, he can do this, among other things, with a sigma which is not C3, it is only C2, and the sigma 2, so you remember this is delta sigma sigma, which is of class C1 plus gamma, so gamma between 0 and 1. So I I think that we can adjust our computations to this setting, but I didn't have time to do this in the last 7 days. So I only managed to add this final line. Actually, this paper by Antoine is quite interesting, so I'm trying to read it in depth. Yeah, so there are some things which I am learning after so many years. I am feeling my lacunes in my general culture. So, for example, the fact that these rough differential equations are, I didn't prepare a slide on this, but the nonlinearity which maps so a control path to another control path, sigma, okay, y to sigma of y, if you want. This is essentially of quadratic nature, whatever the assumptions you take on sigma. This is somewhat different from the ODE setting, and this has some consequences. So that's why some estimates are sometimes a bit delicate. So that's quite interesting. Okay, but again, so this is what makes the transition from local to global a bit delicate. Okay, and that's why maybe these weighted norms can help to make this simpler. Okay, so in fact, this is what I had prepared. Now Carlo has prepared so longer slides than mine, essentially. So I can stop and leave him to discuss what he prepared. Thanks a lot.
Thank you, Lorenzo. Thank you for your nice talk. So now we have the discussion by Carlo Bellingeri.
Okay, Carlo.
Yep.
Let me wait a second. Okay, second. Okay. Do you see my screen?
Super. Yeah.
Okay. Now
So
let's reviews.
Yeah. All yours, Carlo. Whenever you want.
Okay. So. Okay, thank you very much, and thank you to everybody. It's also a great pleasure to be here. It's especially so. In some sense, it's like going back to Paris. So where with Lorenzo we did so this sometimes a lot of seminar and a lot of discussion related, and so to his problems. And so I hope that now we are probably in 70, but so some discussion went good, some discussion went not so good. So I hope that this time this discussion interests maybe someone else also than me and Lorenzo. So I also wanted to discuss in this this really comment about so what's really, in my opinion, what's really going in the Rothbard's business, no? So it's like that is what I call a renaissance for Rothbard. So because usually Lorenzo's talk is part. So we have seen that some people of regularity structure, the SPD community, are taking again some interest in Rothbard. That looks quite interesting. And so because the fact that like since 2013, so we have seen that in regularity structure, there were, so that was like this explosion of regularity structure. And nowadays, it is able to treat some very, very complicated and fundamental and really complicated equation. No? And you will see in AJ's talk, no? If 10 years ago, I will tell you that now it is possible to do stochastic quantization on Young-Mills theory, maybe 10 years ago, people will be a little bit skeptical, but now it is possible, and it's a kind of a great achievement. At the same time, the study of this new SPDs has led to new other questions, to challenging questions, and this question are also interesting to rough paths. So in some sense, we have also a back forward, because usually there was a time where we always think to rough paths as a special case of regularity structure, and so as an example. And it seems that in this case, it is also some new contribution. And the study of a priori estimate is really an effective example to see this pattern. And I want to discuss about this topic. And so what I mean by an a priori estimate, it's like that if you have a controlled equation, usually, so like this, I'm kind of very general what type of equation, just you have basically so two types of norm to study some a priori estimate, and you will have like some stochastic norms, like I tell you here, and these norms are very usual in stochastic calculus. And of course, and I call them stochastics because in order to have some estimate, you need some good stochastic theory behind. So like Burkholder, Davis, Gundi, and you need some probability behind it. So this estimate holds true because X is a specific, is a stochastic process in some specific class. And also you have analytic norms when the source is Roth. And in this case, you can take a really much more general. So it's generically Roth, and you have these analytic norms like the Hölder, the variation, and Benson. So usually stochastic norms are stronger because they usually lead to global estimate, but they work on a specific class of processes. Instead, the analytic norms apply to a much more general class of processes, but they are local. So meaning that they depend on T, and so you have to do this. You have to do these arguments of local contractions and then to global. So you have also this counter side, but at the same time they apply to a wider class of processes. Okay, so in some sense, this kind of framework, which is a typical for Roth analysis, can be also, so it was also part on singular SPDs. But at the moment, a complete theory to obtain stochastic a priori estimate on singular SPDs is still missing. So this is something like what is called the Ito calculus on singular SPDs, which is so some dream of Lorenzo that also gave to me and Henri, probably who is in this session. And so this is something that a main motivation, so and a possible motivation for this singular, this calculus on singular SPDs might be a motivation for that. And so the idea, so in order to circumvent this problem, the idea was like to introduce weighted norms in a very refined way. And this was done with some very, very nice papers for the 543 equation, where there is globality in space and also on the full space, and so in all the time and all the space in some sense. And there are this very, very nice paper by Murat and Weber and Moana Weber. Also, probably I don't know if I mentioned all the contribution. This is what I look, and maybe I forget, and I apologize for that. And also from Gumidelli and Hofmanova to obtain global solution. And this idea, and so this is an idea that comes from this regularity structure and singular SPDs, but seems promising to study again rough paths. And this is really the idea of putting weighted norms, to use these norms to study some equation, but in a rough path setting. And so this is like, this is, I tell you, Lorenzo did not publish a paper. We had a nice discussion, and by looking at the paper. So I think that this talk and probably the contribution, so it really gives you two main ideas. The first idea is the introduction of these two norms with this parameter tau. And this is very important to describe this local behavior. So in some sense, it is possible by paying the price of a parameter tau to describe this local behavior and try to match with the other global result in order to understand it better. And in some sense, I found nice this unified approach, to pass from local to global, and especially when sigma is not bounded, and simplifying many technical results. So some sense, so it's in the recent version of the Fritz Heirer book. There is a well-detailed account, and so I also discovered this paper by Antoine Léger of 2012, and also I also mentioned this paper with Nicolas, Peter, and Anna, where it's not really related to this a priori estimate, but we really had to work with the Roth differential equation, and we really have to work also technicalities to look at this equation on any gamma, and you have some technicalities, and this paper really seems to treat them in a unified and an elegant way. Okay, so in some sense, this is not, it's very nice because, as I tell you, there is, in my opinion, this sort of renaissance, because there are new results related to a priori estimate, and it seems that so this business of raw paths is still on action. And I would like to mention, for example, three main contributions in the literature that are the Roth-Grumman lemma and on-reflect Roth differential equation. And so this Roth-Grumman lemma allows you to give you this new a priori estimates, and it's there are also some nice paper. This paper by Hofmanova, Guminelli, Tindall, and Deya. Also, this approach to 543 is also related to Roth differential equation, and with this concept of coming down from infinity. And there is this nice paper by Bontefoy, Chandra, Monin, and Weber, where they studied these techniques on the 543, but they study back on they study in the Roth path setting with very interesting result. And also, I would like also to mention the stochastic Soin lemma, and there is this paper by Peter, Antoine, Lé, that they had also to deal with this mixed system of where you have a Roth term and a stochastic term, and they had to also to put down an interesting machinery, mixing norms of the stochastic nature, and these are really new techniques, and I think they are still working on that because somehow they are technical, but they're really an interesting contribution, and it really revitalized a lot the research, the discipline, a little bit of Roth paths. And first of all, I will also mention that these first two techniques are also some deep connection with singular SPDs and Roth PDs. So meaning that they were studied. I mean, they had some sense also this Roth-Grumman lemma was also applied to Roth PDs, and now so they have also some connection with PDs, and there is really what I was mentioning at the beginning. So the fact of passing from a PD perspective to Roth paths setting. And okay, now I have just a couple of questions for Lorenzo. So the first question is it is possible so to apply these norms to study from a pathwise perspective some solution of SDs with singular drift, because I know that your passion for Bessel processes and maybe so the fact is by studying, by having a good understanding of what happens on this like normal drift, what happens maybe when I have a singular drift. And so maybe you can just do some localization argument to study that, and maybe you might find some new properties on the Bessel processes and might be interesting. And so, second question, I would like to ask if there are some interesting links of your result with the techniques that I mentioned here. So they are part of these new methods and new tools. And maybe there are some interesting links with this norm. And you also mentioned this link with the stochastic lemma. Maybe it holds with the stochastic sewing, and maybe, I don't know, it might be interesting. And also, of course, this question are, this is maybe technical and this is much more general. But, if you know how to extend your result to regularity structure, and if, in one day it is also possible to prove global well-posedness, to find some condition to have a global well-posedness for the geometric stochastic heat equation, your recent paper with Ivan, Martin, and Franke. So maybe if you want to discuss the perspective, how to study this type of processes, that will be a huge goal. But I don't know, just these are some interesting questions that I had by looking at your talk. And if you want to discuss it, it would be nice. And I thank you, everybody. So this is a shared discussion with Lorenzo. Thank you very, very much.
Yeah. So Lorenzo, do you want to say something about this? Maybe?
Thank you. Thanks, Carlo. Well, now I don't have the questions anymore.
I can, okay, don't worry.
Okay, you can consider these as questions to everybody. So I can give just my opinion. So the first one, I don't think so. So it seems to me that so I know, like Bessel processes will need more than that. So okay, for people who are say fan of Bessel process as I am, so in fact the problem is still for a dimension between 0 and 1. So that's the case where there is still some interesting questions. No, I don't think that it would be so easy. For the second question, I don't really know. I have to apologize for my ignorance of all the papers that Carlo has mentioned. So I can't say anything interesting about that. So about the third question, again, no, I don't think that the global well-posedness for that equation can be proved in such a simple way. So of course, regularity structures are a bit like rough paths in infinite dimension, but then the coefficients become so singular. So the sigma, what would be the sigma, is far from being Lipschitz, so on. So that I don't know. I mean, if there are a priori estimates in that setting, that would be really a great result, much deeper than what I have presented. At the moment, I don't see any way to do that, but I'm not saying it's impossible. I'm just saying it would be
I also put the remarks here, just to say, remarks, so they're not really tight question. You have to say yes, but there was also maybe an occasion to everybody to contribute and their opinion. So, but thank you very much for your remarks and to this question.
Thanks, Carlo. And by the way, I can also repeat what Peter wrote, that what I said several times, that I didn't claim any novelty. Maybe just the formulae contain some novelty, but the results are not new. So Oleg is writing something in the chat. Okay, it's not a question for me. Excellent.
Okay, thank you very much. Okay, now I see it. I see it. Okay, yes, that's okay. Yes, yes, yes. That might be interesting also to put also this weight onto the singular weight, and the fact. So also that paper also comes also to apply from this point of view, so to apply regularity structure techniques to a Rothbard setting, and it might be interesting. So the fact it's like I was thinking about some equation, some model where this is interesting, and at the moment I haven't found yet. So if you want, we can discuss it, but it might be interesting also. Maybe it might be an interesting key. There would be norms with 2 parameters, and you can play with them. Why not?